It has a state-of-the-art excellent performance, exceptional training time cost efficiency, and this is totally open source. You got it right. We are talking about the novel large language model Deepseek. At the end of the video, we'll mention some of the benchmarks that highlights its exceptional innovation. But before this, let's see the secrets behind its success. Mixture of experts, mixed precision training, reinforcement fine-tuning, chain of thoughts, and knowledge distillation. Those 5 concepts are the main pillars of the Deepseek performance and efficiency. Let's discover them together. Firstly, we start by the mixture of expert architecture. To understand this, let's imagine a little boy who has a pain in his tooth. He went to the hospital where there are multiple specialists. He was wondering which one to visit or if he should visit all of them. For that, he finds the nurse at the reception who will make a general examination of his symptoms and based on which she will forward him to the dentist, who has the exactly needed expertise to provide the necessary help fastly and precisely. So the mixture of expert architecture works exactly like this. Instead of using all the LLM parameters to provide an answer, an intermediary gate, called also the network gate, will determine based on the prompt which expert is the most qualified for this task, and it will activate only his parameters during the text generation. This ensures both efficiency and precision. Now, although we ensure the relevance of the selected parameters, the hardware availability is key to maintain this theoretical precision in practice. Here comes the precision cost dilemma. If we encode the parameters on 32 bits, we get a good precision, but along with high cost and processing time. On the other side, encoding them on only 8 bits would reduce significantly the precision, but also reduce the cost and time. So is there any trade-off to make? The answer is yes, using the mixed precision training introduced in Deepseek paper. Instead of encoding all the parameters on 32 bits, we encode on it exclusively the most important ones and allocate only 8 bits for the rest. By that, we switch from the over-precision to the exactly needed precision. Now, with this theoretical and practical efficiency in handling model parameters, we get face to face with the main challenge for LLMs and natural language processing in general, which is the text pattern challenge. This means to ensure that the LLM extracts enough text patterns to provide good answers, we must afford a huge amount of data and the training time. So the question, is there a way to train the model on less data while achieving a kind of transfer learning through injecting to it some of the common text patterns directly in the core of the model, keeping the same performance? The answer is to use reinforcement learning. Let's see how it works. Our starting point is an LLM pre-trained on some amount of data. We use it to generate some text, which we group and rank. Then we leverage all of this to fine-tune the model using a reinforcement learning technique called GRPU. We repeat this process until we get high quality output. Let's see that step by step. The first step is data generation. We provide the LLM with some prompts and it will generate an answer multiple times until we have good set of prompts where for each one corresponds multiple answers. Once we have the model's answers across diverse domains and different tasks, we divide them into small groups based on similarity to track how the model performs in each domain. Then within each group, we assign at each answer a rate based on some metrics like readability, correctness, and relevance. This process is called ranking or also called rewarding. So far, We have the answers of the LLM grouped based on similarity and ranked according to their quality. We use them to fine-tune the model through updating the mixture of expert architecture parameters to achieve two main targets. On one side, we need to standardize the output quality within the same group, ensuring domain stability, and on the other side, maximizing the average general performance across all groups. Using the group relative policy optimization, we ensure that our model captures efficiently the text patterns and it is ready to deliver high-quality answers. One of the qualities that we seek in large language models is the good reasoning capability. Let's say we want to resolve this equation. You can think about it for a while. Could you find any solution? Let's start by using a simple and direct way, and let's see where it will lead us. We apply logarithm function on both sides to extract the x. If you think about it, this path seems to be blocked. And for LLM, if it decides to continue and force the result, it will most likely hallucinate and generate wrong results. For that, while training the model, we encourage it to take a step back to review its reasoning method. Here comes what we call the aha moment. This means that the model becomes capable to recheck himself and suddenly discover that this way will lead to a mistake, figuring out the smart idea that resolves the problem. So in that case, if we divide by 9 to the power of x, we manage to obtain a better form where when we let t be equal to 2/3 power of x, we get a quadratic equation that is easy to solve and we deduce smoothly our solution. What we did now is what Deepseek paper called the chain of thoughts method. So far, our LLM provides domain-oriented answers thanks to the mixture of expert architecture. Its parameters are encoded with the exact needed precision, fine-tuned efficiently using reinforcement learning, and empowered by wise reasoning capabilities. The only thing is that it's still too big to fit into the memory of a personal computer. To ensure conserving the maximum of performance while compressing it into a smaller model, we use a technique called distillation. In that method, the big LLM serves as teacher to a smaller LLM, and this by using the teacher answers as labels on which we train the student to improve its capabilities. So at the end, we obtain a model that fits easily into a personal computer with a respectful performance. It's time now to look at some of the Deepseek's benchmarks. We start by Codeforce's benchmark, where the model competes with a number of participants on coding problems. We see that Deepseek R1 performed better than 96.3% of competitors, close to OpenAI O1 model released in December 2024, and better than the other models, specifically GPT-4o and Llama 3.1. The second benchmark is called Massive Multitask Language Understanding, which measures the LLM knowledge in different general domains. In that metric, the 5 models got reasonable accuracies. For Deepseek it is 90.8, a bit lower than OpenAI O1 model, but better than all the rest. The third one is called GPQA Diamond, or also Graduate Level Google Proof Question Answering, which is a challenging benchmark designed to evaluate the ability of AI models to answer high complex domain-specific questions. Those questions have the particularity that they are difficult to answer using simple web searches, and from there comes the name Google Proof. The general model's performance decreased significantly compared to other metrics. OpenAI O1 performed the best with 75.7 of accuracy, then Deepseek R1 with 71.5. The last metric is called Math 500, where the model is given 500 challenging math problems to evaluate its mathematical reasoning and problem-solving capabilities. Here Deepseek R1 surpasses all models with 97.3 of accuracy, and an important thing to note is that the distilled version of Deepseek R1 surpassed also most of the models, getting closer to OpenAI O1 while it has only 32 billion parameters. We get to the end of our video, so thank you for watching. I hope this has been insightful for you. If you have any questions or suggestions about future topic, the comment part is yours and sky's the limit, so don't hesitate. Thanks and see you soon.